Let us discuss the distribution, which is the Poisson. In this, we are derivative or we can derive the Poisson's distribution. When we are using this Poisson distribution means this Poisson distribution can be derived as the limiting case of binomial distribution. It is the limiting case of binomial distribution. In the binomial distribution, the binomial distribution can be derived b of x comma n comma p is equal to ncx p power x q power n minus x. Here x is the successive of the probability. Here p of r, it can be defined as the p of x. P of x is nothing but probability of the small x successes. In this, x can be success of the any event. In this, we are using the only two. One is when we are using the binomial means either it is success or failure probability, we are using that one. In the binomial distribution, the limiting case is the Poisson distribution. In the Poisson distribution, what are the limits means the main thing is small p is very small. When it is very small, then the relation is q is also equal to 1 minus p. But here p is very small is the first case of the following conditions of the Poisson distribution. Second one is n is very, very large value. And the third one is when small p is very small, when n is large, then NP product is equal to some finite quantity. That finite quantity, let it be lambda. That is the value. Finite quantity means that is the number. So when this NP relating with the lambda of the finite quantity, then lambda is the parameter of the Poisson distribution. The lambda is called the parameter of the Poisson's distribution. How to derive the Poisson distribution means it is the special case of the binomial distribution. From the binomial distribution only we can derive the Poisson distribution. The binomial Poisson distribution simply it can be defined as P of r equal to e power minus lambda into lambda power r by r factorial. This is the distribution. Here small r is the number of success. N is the finite number of, that is n is the number of independent trials. Small n is the number of independent trials. In that small r is the number of success from the independent trials. From this, the Poisson distribution can be derived as P of r is equal to e power minus lambda, lambda power r by r factorial. Here lambda is the Poisson parameter. Then the relation of the lambda is equal to NP equal to lambda. This is the definition of the Poisson distribution. How to derive the Poisson distribution? That is the derivation of the Poisson distribution. The derivation of the Poisson distribution can be derived as the Poisson distribution can be derived as a limiting case of the binomial distribution under the following conditions. What are they? Small p. What is small p? The probability of the occurrence of the event which is very small, and n is very, very large, and n is the number of trials as n tends to infinity. Here NP is a finite quantity. We say that NP is equal to lambda. Lambda is the parameter of the Poisson distribution. These are the conditions of the Poisson distribution. From that only we can derive the Poisson distribution. Here by the binomial distribution, the probability P of r or P of x equal to r means in that small r successes in a series of the independent trials n, which is given by P of r equal to NCR P power r q power n minus r. We know that q is equal to 1 minus p, then q is replaced with 1 minus p whole power n minus r. Here NCR is nothing but n factorial by n minus r factorial into r factorial into p power r into 1 minus p whole power n into 1 minus p whole power minus r. Here, the expansion of this n factorial by n minus r factorial means n into n minus 1 into n minus 2 into so on, n minus of r minus 1, n minus r factorial by n minus r factorial into r factorial p power r 1 minus p whole power n by 1 minus p whole power r. Here n minus r factorial, n minus r factorial get cancelled. It is equal to, that is p of r is equal to n into n minus 1 into n minus 2, so on, n minus r minus into minus plus 1 by r factorial into p power r into 1 minus p whole power n by 1 minus p whole power r, which is the first equation. Let it be first equation. This is the expansion of the binomial distribution. In this, we can substitute the value, that is the finite quantity np is equal to lambda. From this, n is equal to lambda by p, substitute in above. Here, p of r is equal to, n is nothing but lambda by p into lambda by p minus 1 into lambda by p minus 2, so on, lambda by p minus r plus 1 into p power r into 1 minus p whole power n by 1 minus p whole power r by r factorial. Okay. Here, taking the LCM, lambda by p, lambda minus p by p, lambda minus 2p by p, so on, lambda minus of r minus 1 p by p into p power r by r factorial 1 minus p whole power n by 1 minus p whole power r. Here 1, 2, 3, so on, r minus 1. Here 1 to r minus 1 and here 0. That is nothing but here all are get cancelled. This p 1, it's a 0, 1, 2, r minus 1 means 1 to r minus 1, 0. So that is r p's and p power r get cancelled. It is equal to lambda into lambda minus p into lambda minus 2p into so on, lambda minus of r minus 1 into p by r factorial into, here we can write it as in the numerator 1 minus lambda by n whole power n. Since np is equal to lambda, from this p equal to lambda by n by 1 minus p whole power r. So here p of r is equal to lambda, lambda minus p, lambda minus 2p, so on, lambda minus of r minus 1 into p by r factorial into 1 minus lambda by n whole power n by 1 minus p whole power r. Here n is very large, in that we have the relation from the second condition n tends to infinity. When it is n tends to infinity, then small p is equal to lambda by infinity, it goes to 0. Why? Because small p equal to lambda by n. So here p is the, substitute the 0 value in the above expression, then p of r is equal to lambda into lambda so on into lambda up to r times by r factorial, And here this is the n related value. So we apply the limit n tends to infinity 1 minus lambda by n whole power n. Again limit here p tends to 0 1 by 1 minus p whole power r. Why? Because we have the relation as n tends to infinity. When we substitute infinity, p is the 0. Here it is equal to up to r times means lambda power r by r factorial. And we have the relation 1 minus limit n tends to infinity by the limit and continuity. Limit n tends to infinity 1 minus lambda by n whole power n is equal to limit n tends to infinity 1 minus lambda by n when it is also minus n by lambda whole power minus lambda. We have the relation in the limits and continuity. Limit n tends to infinity 1 minus x whole power 1 by x is equal to e power 1. Here this is whole power minus lambda is nothing but it's e power minus lambda. When it is we are eliminating only 1 minus x whole power 1 by x, that is the exponential only. This part is exponential power minus lambda. From this we can write it as in the place of this, that is e power minus lambda, and as p tends to infinite, p tends to 0, then 1 by 1 minus p whole power r, it is equal to 1. Limit p tends to 0, 1 minus p whole power r is equal to 1. 1 by 1 is equal to 1. So 1 by limit p tends to 0, 1 minus p whole power r. It is equal to lambda power r by r factorial into e power minus lambda into 1. Therefore, p of r equal to probability of small r success is equal to e power minus lambda into lambda power r by r factorial. This is known as the Poisson distribution. This is known as Poisson distribution. It is the derivation of the Poisson distribution.